So let me know when you're
You're live.
recording in progress. Okay. So welcome, guys. Today is the first GEM, General Education meeting for all of you interested in learning model rocketry, the basics of model rocketry, the structure of it, and I know that there's people in the meeting that are also interested in certs. My name is Alex Sanchez Ira. I am currently the lead of the avionics and recovery team for the IREC competition that we're doing. Um, if you guys aren't in the team, you guys should probably come to my meetings. It'd be a good addition. So, Joel, Bryce, introduce yourselves.
Yeah, so I'm Bryce, current VP internal, and also the lead of propulsion right now.
Hey, I'm Joel. I'm the president, previous structures and manufacturing lead.
And yeah, thanks for coming. We have a few announcements on the next slide that we could announce. That's mail. Okay, so today is going to be the introduction to model rocketry. It's just all the basics, the structure of what a standard rocket looks like, motor configurations, a little overview of like the flight dynamics in terms of center of pressure and center of gravity and whatnot, and then a little open rocket demo so that we could get you guys familiarized with the program that we use mostly to um, simulate and check all the components of our rocket and make sure they're stable and safe to fly. Next meeting, which is on the 10th of February, is going to be all about flight dynamics, and that's going to be with Bilal. If you guys don't know Bilal, he's a fun guy. He's very knowledgeable, and I'm sure that you guys will grow to like him. He's very, very experienced. He has a level 2 certification, and he has designed level 3s. So you have a lot to learn from him. Next, the meeting after that would be structures with Joel. Joel's the president of the club, as he just said. So, clearly he has a big brain too. And then after that would be avionics and recovery with Bryce. And then another thing I want to mention is that these meetings will be in person, right? Most likely. Probably.
I'll try get us a room in Marston. I can't get a big room because it's still during class time.
Uh-huh. So the reason that this one's online is because I'm in Atlanta, Georgia, and I'm not in Gainesville. So you guys are gonna have to deal with Zoom for now. So hopefully you guys could get some interaction in person later down the line. And then after we go over all the genuine education and you guys are caught up to speed with how a standard L1 works, we're going to be working on designing your L1s, going over them, doing design reviews, and then begin manufacturing so that we could actually get some certifications pushed out and stuff like that. So without further ado, we could just introduce the basic format of what a standard rocket looks like. So when you have your standard L1, it's typically, not that big. They range from 3 to 4 or 5 feet, depending on how big you want to do it. Of course, design is up to you. But to start off, you have your typical nose cone, which when you're designing it, the shape of it is up to you. The recovery system, which consists of a parachute, a shock cord, a bunch of links to hold the rocket together, an airframe, obviously, which is the body tube of the rocket. You could vary in diameter depending on what design you want to go for. Then we have a launch lug or rail buttons, which are designed to hold the rocket in place steady so that when it launches, it goes straight in the direction you want it to and it doesn't twist or turn in any bad direction or hit anyone in the face and cause damage. That would be pretty bad. Then we have the fins and the motor mount, and the motor mount also has a motor retainer, and we'll get into that in the next slide with the motor retention system. So the most basic component of the assembly for the L1 rocket is the motor mount assembly that encases your motor that's going to launch the rocket into the air. We're going to go over this extensively. Actually, this diagram is very important because you guys are going to manufacture this yourselves. The motor mount assembly contains a motor tube, which encases the motor, centering rings to transfer forces from the motor tube into the airframe and the centering rings so that your stuff doesn't break. And then the motor retainer, which holds the motor in place and doesn't have it launch out of out of the rocket or fall out during flight. Very, very important. In the motor tube, there's also, we could add an addition of fin cans. Fin cans are also a really great addition. For those of you who don't know, I don't think we have a picture in the presentation, but a fin can is basically a 3D printed cylinder with slits in it to put the fin inserts to make it gluing easier and to make the structure stronger. We'll go over that later down the line when we do get to manufacturing stuff. But for now, that's all you need to know about the motor mount assembly. So we can go on to the next slide. So in terms of motor setup, once you have your motor tube and centering rings properly epoxied in the locations they go, according to obviously the specifications of the motor you have in your rocket, you do epoxy it to the inside of the airframe, and then you wait so that it dries. You cut slits into your airframe so that you could pass fins into them all the way directly to the motor tube, and then you epoxy those with to the airframe with fillets on the inside and on the outside. It's basically very standard. You just could see that everything's kind of simple right now because there's nothing too crazy to go with. One thing I also want to mention is that these materials, usually the centering rings are made out of some type of wood that we have in stock at the SDC, as well as the motor tube and the fins. These materials are all there for you to use and design. So it's pretty simple. You have stage 1, which is the basic assembly. Stage 2, which is the epoxying inside the airframe. 3, doing your fin inserts to the motor tube and the slits inside the airframe, and then gluing it overnight. Without the motor tube, without the fin cans, this process is a lot harder to do because you have to do one side at a time, and the fin cans let you glue all the fins all at once. So, but we'll get into that later, as I said previously, because we're not near manufacturing, and that's not really relevant right now. So,
yeah. So, if you need like a quick summary of what's going on here, just from like a kind of upper level view, this whole setup here is basically holding all of the propellant that you have in your motor. So if you'll remember, there's that really long airframe that actually doesn't contain much except for the recovery system and any sort of payload we have. All of the actual propellant for the rocket comes in this little tube, and we put that tube inside this tube basically. And using this smaller tube, we can kind of have retention mechanisms to keep that force from leaving that smaller tube. And we could use that force to propel the rocket. And then we also have fins down there because we'll talk more about it in flight dynamics, but yeah, just an upper level view of what's going on with why we have this tube, I guess, why it's called the motor mount.
And by the way, guys, if you guys have any questions about anything and you're confused about anything, please let us know. That's why we're here, to teach you guys the standards. Don't be scared to speak out. We're in a small group of people, so we could get to everyone's questions. Don't be afraid to jump out and ask about any confusion. I want to ask you guys, does this all make sense to you? Is there anything that you have doubts on right now? We don't want to be moving too fast.
I have a question. So for the bottom left, where it says cutaway airframe with the TTW fins glued to, those are just like the thing you glue to the motor mount tube is just what holds the fins, right?
Yeah, so basically the fin has an insert. If you see it,
yeah, it kind of like slides in between.
You want to hover over it, like the fin insert right there, or drive if you want. Like it's right, like it slides into the. You basically, what you do to the airframe is that you make a slit in it. You cut a hole in it, and then your fin has an insert that slides into the airframe, and then you'd epoxy that end onto the contact surface of the motor tube. And then you want to epoxy the inside of that slit where the fin touches, and the outside as well. So you can see that Joel highlighted it in the last picture, how that red line, that's where your epoxy would go. And then the same on the inside.
Yeah, so what you're
sorry.
Yeah, so what you're asking is like essentially about the mounting method of the fins, I'm assuming. So the way that we generally do fins is we do them through the wall, which is what TTW stands for. So through the wall mounting is the most is the most used way of mounting fins. It's also probably the most secure way of mounting the fins, because what you do is you have your like circle airframe, right? And the purpose of through the wall fins is, like Alex said, you cut a slot through it. So you cut like a small little excess where the fin can fit through the airframe, which is why it's called through the wall. So then what you're doing is you're cutting the fin so that it goes through the wall of the airframe as far down as it can up until the motor. And then from there, like you said, there are these little like sections where you would just epoxy it. So then your fin, it now has like 3 points of contact where it is epoxied to the airframe, making it probably as secure as it can possibly be. So like that's just a really not in depth, but that's these manufacturing methods. We'll go over it more like as we progress, but we're trying to get you like for the time being right now, just an overall holistic view before we start going in depth so that you can understand like each individual subsystem and like purpose of each little manufacturing thing. After this meeting, I can show you a SolidWorks, which would probably help tie in everything that we're going to go through on these next few slides.
Yeah, we could even, we could even sub out the open rock. Should we sub out the, after the meeting, we'll figure that out.
Yeah, after the meeting, so then we'll show you everything first to give you like bits and pieces. It'll be pretty, maybe a little challenging to think of it as a whole since we're presenting it to you as sections, but we'll show you the Open Rocket, which is a program that we mainly use, and then from the Open Rocket, we can show you the other ways like get a better holistic view of the rocket.
And if you go back to like the overall diagram of it, so they could just orient themselves real quick. That part that we're talking about is where the fins are. So you guys could just picture it. That part that's like dotted lines down there, that's where your motor assembly would be in. So your motor tube, your rings, and would be epoxied inside there, and then you put your fins with through the wall. Okay, let me go on. So that's basically the standard structure of the rocket. Nose cone, parachute, body tube, your shock cord holding everything together, your motor assembly, your centering rings, and your fins. The really important thing that we have to get down, though, this goes a bit into the flight dynamic side of things, but it's just the overall general overview of things. Are the CG and CP, which do any of you know what that is right now without reading the screen?
Center of gravity and center of pressure.
Yeah, there you go. Center of gravity and center of pressure. So these determine how your pitch motion of the rocket works. So basically, the stability of your rocket. The center of gravity is synonymous with center of mass. If you guys have taken physics, you guys know what a center of mass is. The center of pressure, some of you guys may not know what that is. It's where all your aerodynamic forces are concentrated, your moments, your torques and stuff like that are produced through forces onto your rocket, like wind. They all concentrate at this point. Oh, words. Did you put that there?
Yeah. So basically, the summary of this is to get the stability of the rocket, just in general, because when you get over to Open Rocket, you're gonna be looking at the stability and be like, why is it so low, or how do I even edit this? Try to make mass closer to the top of the rocket, and try to make pressure closer to the bottom of the rocket. And you increase pressure at the bottom by making the fins bigger, increase the mass at the top by making more of your structure higher up. But yeah.
So yeah, we go into that later, I think. I'm not sure, but I'm pretty sure we do. But yeah, they tend to be one body tube diameter apart from each other. That's just the standard. And like we mentioned, on Open Rocket, which is the software we use, we could find both of these numbers and the stability of the rocket according to them. So just to go a bit more in depth, we have a little diagram to show you guys how the CG and CP are affected. So
I have a question.
Uh-huh.
Oh, does someone else have a question? Oh, okay, well, why is the center of pressure not closer to the nose cone?
Because think about it. What do you think would affect most of the aerodynamic forces on the rocket? Like what's the big player in here in these things?
Like the force or like part of the rocket?
Yeah, which part of the rocket affects the What do you think affects the CP the most, the location of it?
I mean, I thought it'd be like the nose cone because that's where you like are piercing the air, so to say. You know,
That's a good assumption to make, but does anyone else have any idea what affects it the most? I think Bryce mentioned it like 2 seconds ago.
The motor
No, the
or the
fins.
fin.
The fins. And if anyone can you guys, if you guys want to explain that a little better than me, because I'm tired, but the fins do affect it the most. And the CP's location is also affected massively by the fins, because your fins affect how your sorry, there's my roommates just walked in. So can you guys take over while they're making noise? I'm sorry.
Yeah, so basically the fins themselves, I'm a mechanical engineer, not an aerospace engineer, but generally as you increase the size of the fins, you kind of increase the surface area down there. And that causes more pressure to be present down at the bottom, and that moves down the center of pressure. It's a fine balance trying to get the size of the fins right, especially since you're kind of increasing mass near the bottom when you're increasing the fin size. But using the simulations, the fins are one of the most editable parts of the rocket, since we usually just cut them out of like a 2D plate. So it's one of the easiest ways to change the stability of the rocket, as you'll come to find out.
Yeah, and we want you guys, when you guys do eventually start designing your own thing, be creative with it. I know that Bryce's, when he launched his L1, it looked like an egg. And it worked out pretty fine. So yeah, and then another thing we're gonna get into in the next slide and the next couple slides is that the importance of how the CP and CG location affect your rocket and its motion. So I mean, we could go on to the next one, unless anyone else has any questions. Does anyone else have any questions? Awfully quiet in here.
So the specific reason why Bryce said CG should be higher and CP lower is that there is a rocket equation that gives you the stability of that will give you the stability, which is a function of the CG and CP. So like specifically the stability will influence the way the rocket performs. And there is a desired range where we want that stability to be in. And the way to achieve that is by controlling like the two factors, which are center of gravity and center of pressure. And you did have a comment, which was that the nose cone you believe should be the most influencing factor of like the center of pressure. And while the nose cone does like pierce the air, something to consider is that the center of pressure is more of a function of like the drag of the rocket. So you have the skin drag caused by the surface, and then there's most of the surface area is at the fins, just because of the way the fins are, right? It's just a protruding surface. So the thing with the nose cone is that as it pierces the air, the act of it piercing the air is generally like pretty smooth because of the shape of it, and also because of the speed at which the rocket is launching at. So generally with lower powered rockets, we won't be going too fast. We're going about half Mach, which means we're going about half the speed of sound. So generally speaking, when you're going at low speeds, right, you're just going through the air will just move around the rocket. As you go higher and higher speeds, the air will have a harder and harder time moving around the rocket fast enough. So then what happens is when you hit like Mach 1, essentially, you're moving as fast as the speed of sound. The air doesn't have enough time to think to move around the rocket, which is why you have shock waves, because the air is just moving too quickly. So then it has to like drastically change speed to get out of the way of the rocket. The thing with that is once you start going at those speeds, these assumptions that we're making using these general like basic rocketry equations, they will break down because they no longer fit within the assumptions that we generally make. So like going too fast while like while we are while going really fast will change the dynamics of the rocket, it's not necessarily something that we worry about because we're going much slower than those assumptions will influence the dynamics of the rocket. Okay, that's a little maybe too in depth for just trying to explain it. I'm sorry.
And we have diagrams that also show a bit of this to try and make sense of it, because for those that are being introduced to it, it might not make too much sense now. So I mean, if you guys want to go to the next slide, I'm sure that it'll clear up a bunch of what we just talked about. So, and there's a lot of text and stuff over the diagram, but how the CP affects the rocket, as you can see during the flight. There's the example we were talking about, how the CP being below the CG and the CP being above the CG and how it affects it. We know that during flight, when you're in flight, you're obviously going to have wind speeds going in. It's not going to be optimal, like in a physics 1 problem that you just don't take into account friction or the wind on that day and what's going on around in your surroundings. But when you're on flight, when you're on the launch pad, there's obviously going to be wind conditions that cause your rocket to move in ways that you don't want it to. If the CP is in front, basically what happens is that the force is centralized at the front of the rocket, and then it will go in the direction of those forces causing instability. So basically what it does is that, so let's say the wind hits it from like the left side, pushing it that way. If your CP is in front, the moment caused by that will go in that same direction and cause your rocket to spin out of control. So it basically it's a double. It basically it stabs you in the back twice. So you're not stabilizing your rocket and going back in your flight path. If the force is getting hit by it, it's just doubling in that direction and spinning it more out of control. On the contrary, if your CP is behind, the forces create a torque that stabilizes the rocket back towards the flight direction. So the force acts on it from the left. And then the moment created goes to the right and stabilizes it back into the desired direction of the flight path. So I'm not sure if that makes any sense to you guys. You guys have any questions about that? Did that, clear up any fog that you guys had about the center of pressure being in front or in back?
I can show you guys. I'll give you like a little diagram of your favorite. Everybody loves these free body diagrams.
Mm-hmm.
Right, so you have your center of pressure in the back and your center of gravity in the front. So if you think about it like this, a change in the moment of the function of the rocket will cause the center of pressure behind it to rock. And then if it's in the front, that means the front will rock. So then if CG is trailing behind CP, what will happen is as the rocket launches, you'll have it trailing behind where it'll essentially move forward, right? But the back of the rocket is what will be essentially moving. You'll have the inverse with the unstable rocket, where as it's moving forward, the front of the rocket will be unstable, right? So then, I don't know if you guys are familiar with that. There's a video of a truck pulling a trailer, right? And then it tells you about the way that the trailer is loaded, right? Like you want your CG, you want the most of the mass in the trailer to be forward, then back, because of the way that it amplifies the way that the trailer reacts to it. So like you have the CG in the front and the CP behind it, so that any of the moment is behind the rocket, so that it's pulling it that way, which is like a naturally stable property. While opposed to if you have it in the front, it just is an inherent unstable configuration.
Yeah, a good way of thinking about it is if you have anything top heavy and like kind of long like this. So this is just a piece of aluminum that's kind of bigger up here and smaller down here. If you like knock it from up here, which the CG is lower on this, like you'll see that it goes down. And then, so if you think of this like a rocket, your CG, you could flip if you have your CG wrong. But if you're holding it like this and your CG is lower and you hit it, it'll automatically go back down. So it's always pointing vertical. That's just something that helps me think about it. And yeah, you'll
That's like
find that
head
as you, sorry?
That was big brain.
Yeah. And as you'll see later on, as long as you reach a certain amount of stability, you're super good. But another thing that you could kind of see with this example is that if you push on this body, you'll find that your rocket will go into whatever direction of the wind if it's overstable. So this is something that's like kind of a something we probably shouldn't be worrying about too much yet. But if you have your rocket too stable, your CG is too high, then your rocket will like automatically always coast into the winds very strongly. But for our purposes, it's much more important that the rocket is stable. So when we get over to open rocket and stuff, I'm sure we'll have a little fact sheet about stuff you should be shooting for in your open rocket when you design it. But as long as you're within like 2 to 4 calibers of stability, you're good. But if you're overstable, it'll highly affect the performance of your rocket and make your performance worse. it'll basically always go into wind, such as if you were to push this, like at all. You see how it kind of goes in that direction? But yeah, fun.
Yep. So, I mean, I guess the next slide just reiterates everything that we just explained on this one, because you know, we got ahead of ourselves.
Maybe we
But
should
it's
have read
fine.
the slides a little better. I'm sorry.
Yeah, we got ahead of ourselves, but you know, Rocketry is exciting and we were impatient. So this is basically all we just said. I mean, you could read it on the side. You know, torque axis CG, the lift towards the right, counterclockwise torque, everything. The force is balanced out. You guys don't have to worry about all the fancy jargon of it. It's basically the reason we have the CG in front of the CP is so that the restoring forces of the rocket keep it stable, so that your rocket doesn't happen to kill someone on launch day. Because it's really important, you know, later down the line, safety and stuff like that. So we want to make sure your rocket is stable, because there has been, you know, occurrences on launches from other rockets, at least from experience, where I launched my L2, someone did get hit with in the eye by a small rocket, and they passed away. So that's why all this stuff does have a significance when taking into account like designing your stuff. And then in the next slide, there's a couple of ways that you can affect both your CG and your CP, which you're going to have to take into account when you're designing your own rocket. So moving the CG forward, there's basically two standard ways of doing it. You could increase the weight in the forward section, forward of the original CG. So that'll push your center of gravity forward, or you could decrease the weight in the back part of the rocket where your motor stuff is. But you know, we don't really touch that right now because there's not much to an L1 rocket that you could change back there. Moving the CP back, which is ideal. So basically what this slide is telling you, you know, you either move your CG up or your CP or your center of pressure back. So ways to change your center of pressure, as we mentioned earlier, increasing the area of your fins will drastically affect your center of pressure and your stability. So that's the number one way that at least I recommend to affect your CP when you're designing it later down the line. Increasing the number of fins also affects it because you're adding more surface area in quantity as well. And then you can also move the fins back down towards the lower part of the rocket. The location actually affects it quite a bit too. Is there anything that you guys want to add? Will this PowerPoint be available to see after the meeting? Yeah, and it's also recorded, so we could definitely send it to you guys once we finish up here. Does that make sense to you guys? Do you guys have anything else you guys want to add on there, Bryce, Joel? No.
I have
Silence.
a question.
Okay, go ahead.
What would happen if the CP and CG are too close?
Then if the CG and CP are too close, your rocket wouldn't be stable enough to fly, and then it kind of leads to what we explained earlier, that the forces will just take it in the completely wrong direction, or like push it out of the flight direction, and then it will lead to disastrous stuff. So it's not fun things to deal with. Bryce, I think Bryce wants to mention something.
Yeah, so from like a empirical standpoint, it's generally agreed that you don't have to do this math. OpenRocket does the math for you. But basically you have this distance here, that's the distance away from the CP and the CG. And as long as this length is 2 times your the body diameter of your rocket, or the airframe diameter of your rocket, it's usually stable enough. So that's like kind of empirical. So it's not like there's no like magical scientific formula for it. But yeah, generally that's something that you know, Rocketeers agree on, I guess. And if you have lower than this distance, then you will experience some instability. So if you're lower than 2 times, you'll have instability. And if you have your CG below your CP, that's like catastrophic. Like it like it'll instantly flip around when you're flying it. So don't do that. But yeah,
that'd be very bad. Not fun to deal with either. Anyone else have any questions, any comments on that? Because the next step that we're gonna go into is just showing you guys OpenRocket. If you guys, how many of you guys know what OpenRocket is? I'm assuming not many of you. Okay. Okay. You've seen it. All right. This is good. This is good. This is really good. Okay. Do you guys have it installed on your computer? Okay.
Damn, you had no faith. No faith, Alex.
When people are relatively new to it, I assumed no. Hey, one person did say no though, so okay, we could go ahead and show him how to do that. Joel, can you pull up OpenRocket's website since you're the one sharing screen? You can just download it off that. Aren't there also download instructions on the Slack that Mika sent out? I think.
Yeah, there's download instructions on the Slack. It's for the guy who doesn't have it installed, Asher. It's pretty simple. You just go into the OpenRocket website. You could probably look up OpenRocket on Google, and it's just as long as your computer could run like Java applications, it should run.
Mm-hmm.
Yeah, it's not
Yeah.
bad.
So there you go.
Yeah, so yeah, you need Java, which is kind of funny because Java just got discontinued, I believe, by whoever supports Java, but you'll either need to download it, or if you already have it, then just download this. Sometimes this doesn't work, so if it doesn't work, let us know. I believe we have a legacy version of OpenRocket, which should work. Yeah, so download OpenRocket. I'm assuming since you guys all said yes, majority of you guys said yes to knowing OpenRocket, then I guess we can open it or we can launch it. If you guys, just to put a lot of what
I have a
Alex was talking about.
I have a sample rocket if you want to use it, Joel, since you're the one sharing, or do you want to transfer it?
If you DM me, I can pull it up.
Yeah, I'll pull it up.
I can
So
also show I can show off. I should have some old ones.
Okay, yeah, go ahead. Show off some old ones if you want.
Boy, let's go digging through my computer.
Does anyone have any questions how basic rocket looks like? I know that we kind of breezed through that really quick. I just want to make sure that you guys know that, it's relatively simple. I just don't want to, breeze through it in case you guys didn't have a good chance to look at it. Anyone? Okay, I'll take that as we're A-okay.
You're so organized, Joel. Jeez. You have like 50 different folders for everything, man.
A folder inside a folder inside a folder.
And they're all empty too.
You want me to DM you the file?
That'd be
Just
good.
go to your recent rockets.
It's kind of
Just
funny.
DM you.
I'll show off my cert rocket, I guess.
Oh yeah, go
For
ahead.
one of the old rockets. So I guess cert rocket's the wrong rocket if we want just single deploy, right?
Can we just open the example? I can send you my L1.
Simple model rocket.
There you go. Boom. Although
Okay.
we should probably show them how to add stuff.
Well, before we add stuff, I think maybe connecting this to what we talked about
Mm-hmm.
would be a good idea. And then once we just go over what we talked about, then I think we can start showing open rocket like components. So I guess this is more structures than anything, but if you remember the initial slide that Alex introduced, very first one, right? This is your rocket. You have your fins, airframe, nose cone. I'm assuming when I toggle, you can see this be changing, right? Can you see me switch between OpenRocket and Firefox?
Yeah, I think so.
Okay, so yeah, you have your nose cone, airframe, fins, right? It's like these two pictures are, I think, almost exactly the same. Yeah. So like those are your two components that you have, or those are your components that you have between both of these. And then the very last things that we were talking about were center of pressure and center of gravity. So if you look at the top right of this little screen, you have blue is center of gravity and red is center of pressure. So like these are the two main things that will affect the stability of the rocket, which you can see right here at the very top, stability 2.41. And then like the things that influence are like fins and then the weight inside the rocket. So like there are different criterias that we were talking about, like the very last slide, that's tell you how to shift center of pressure, the red one, and center of gravity, the blue one. Yeah. Alex, what did you want to talk about Open Rocket? Did you start
I just
adding
wanted to
components?
show them how to start inserting stuff and stuff like that. So like if
I can drop screen share.
yeah, you could drop screen share and you can give it to me if you want.
Yeah.
I'll just start a new file so that you can. Host has disabled participant screen sharing.
It's live.
I got it. All right, I got it. So when you open up OpenRocket, the first thing you're greeted with is a blank screen. You're obviously not going to have all of your stuff, but you could slowly start inserting stuff one by one. So let's say we could just insert a nose cone for now. And here you could also have all your specifications for the things. So for each individual part. So you could choose the shape of your nose cone. You could choose the shape parameter. You could choose the length, the base diameter, and the wall thickness. Also the shoulder, which is the part that digs into the rocket. Let's see. Let's just make this a bit bigger. Digs into the rocket, into the insert of your airframe. Let's make this 1.9, just for showcasing. And then this designing part is really up to you. I don't want to get too into specifying what materials you guys could use. I want you guys to actually, come up with your own unique design, and you could get these measurements off of parts at the SDC. I'm not sure. Are we allowing students to go in the SDC, Joel? To go and look at no?
No. If you want to be able to see what components we have, you'll need to let somebody either on the e-board or a lead, because they'll need to give you access to the SEC with their gate code, and then also there's the door codes.
Yeah, so just a heads up on all of these like material selections, and he's kind of clicking around on all of these numbers over here. One of the big problems that happens when anyone ever does like their first design on OpenRocket is they kind of do non-standard sizes for all these things. They're like, oh yeah, my nose cone will be 6 inches long and it'll be 5 inches thick. Well, 5 inches, no, but you get the idea. Basically, make sure that when you're picking these sizes and stuff, you're using actual material we have. If you're off like on something like wall thickness, even by just a little bit, you can throw your rocket off like weight wise by a lot. So you could look up all the materials we have. I'm sure Alex is going to compile a list of all the things we have, like in regards for you guys using to build. But all of the websites that we buy these things off have these numbers for you. So we're not looking at it yet, but they'll have an OD, they'll have an ID, which is your outer and your inner diameter. And they also have your material selection. So you want to make sure you pick the right material. And all of these things are like really crucial to having an accurate simulation. So just random side note for everyone. But yeah, just
don't
make
be
sure.
don't be scared of it though. It's really not that bad to deal with, as long as you like do your research and stuff like that. You could definitely find these numbers generally easily, and then I will make a list with all the stuff we have and what parts we have. I'm gonna be there next weekend, but I'll work with the people I know to get me all the information we need, and to help you guys obviously start doing your own designs. But generally, that's how you would design your nose cone. You pick your nose cone shape, you set your dimensions, and then you set your shoulder. Right now, it's not really too specific because it's for the purpose of showing you guys how to add stuff onto OpenRocket. I'm sure you guys, if you guys have worked with it before, you guys know how to do it already. But for those who don't, and then we could add a body tube, and obviously we could change the body tube length. Let's just make this guy long, because why not? Change the material to whatever. Let's say fiberglass, because we're bougie like that. And then we could close that, or we could set the paint to smooth, because we gave our rocket a sick paint job, and it's looking clean. Then under the body tube, we could add many more things. So this is where you start adding your engines and your inner tubes. Your inner tube is usually your motor tube that you saw earlier and stuff like that. So you add your inner tubes, your centering rings, You adjust the dimensions. Obviously, you make this bigger according to what you're designing and the motor tube that we have in stock, the inner diameter. And then let's see, you can add your fins, and you could change the shape of it too. Obviously, you're gonna have more than one centering ring. I'm just doing this for the sake that you guys could see it. And then you can see how all these components that you start adding start changing your CG and your CP and your stability numbers that are up here. Right now, this rocket is really unsafe. Do not fly this rocket. So you could also add mass components, which is for stuff that's not specified, your parachutes. Usually your mass components are going to be stuff like D-links, stuff like eye bolts and stuff like that, so that you could attach your shock cords and your parachutes to, so that everything stays as one piece and comes down all together and not just crash into the ground. And then you have to dig it out with a shovel, which is not fun. So just to show you another type of rocket, I'm going to open, I think, what my L1 was, which is this one. No, this is one that's really old, actually. Before I even... Is it this one? Okay, this one's way better, I think. It's still outdated, but it gets the point done. This is the mass components that I was talking about. The eye bolts, the D-links, and the eye bolt on the centering ring. These are all mass components that you could add. And obviously, we're going to give you how much these things weigh so that you could make an accurate design. The centering rings, the motor, the motor tube, the motor. I'll also have to show them how to put the motor in, which is the motors and configurations tab. We open a new configuration. Then we select the motor.
Change your open rocket. You're not sharing the right screen.
Oh, really? I'm not. Damn it.
I thought something was weird too. I was just watching the screen.
Yeah. I'm here switching to my outdated L1 model. Is this it?
Yeah, you're good now.
Okay, my outdated L1 model, and you guys don't tell me anything. All right. So what I was saying earlier, that these are all the mass components that I was talking about. D-links. I'm sure you guys know what D-links are. Who doesn't know what a D-link is? Chat. Okay, no one.
What's a D-link?
What's a D-link? Okay. A D-link is let me see if I can pull up a picture. It's basically a link that looks like a D. So, but I know that doesn't really help much. So let me look up a picture just so you guys can. Yeah, I mean he's drawing. They're drawing it right there. So.
My link is huge, but I just Googled quick links. So they're just a component that connects to other components.
Okay, so this is a D-link. Yes, you could find it on Amazon. So basically it's a link that you put, let's say, your shock cord in or your parachute, and then you screw it back on so that it all stays inside that one loop, basically holding everything together. That we use that for attaching shock cords, attaching swivels and stuff to the parachute and whatnot, so that stuff doesn't fall out of line. Let's go back to the L1. Okay, so is this it? No, this is the bad one. This one. Okay, so that's a D-link. Do you know what an eye bolt is? I'm waiting to see. Yes is a no.
What's an eye bolt?
What's an eye bolt? Okay, an eye bolt is this. This is an eye bolt. So basically, you'd attach your shock cord to this. The nose cone typically has one. Then we put one on the centering ring so that we could attach shock cord on this side and shock cord on this side, so everything stays together. Oh, what's shock cord? Yay! Okay, let's look up shock cord. Weep. Shock cord is a cord that holds everything together. Usually of a material that is somewhat heat resistant. So let's look up one that's more accurate to what we're using. Something like this is a shock cord. A cord that is used to hold everything together. And look, a D-link. Everything comes together. So self-explanatory. We tie the ends to the eye bolts and then put the D-links in their corresponding spots so that we could attach the parachute properly, and then an eye bolt on the centering ring on this side. Another important thing that I didn't mention that you guys might not know And I think this is going to be the last Google search, but I'm not sure. A swivel. Let's look up a swivel. This is a swivel. This is for fishing lure, but the swivel helps us keep parachute lines from tangling, and you guys will get into that further down when you guys go into the avionics and recovery section with Bryce. I'm pretty sure Bryce will go over all the parachute and stuff like that, and then the parachute packing and stuff. But there is another component that you'll probably be using in your design. So just to clear up, all the potential things that you could run into. And back here. Okay, so this is what a standard rocket might look like. Stability is 1.47, which is pretty good. Is more than enough for what you're gonna need for an L1 flight. There's obviously fallacies because this is when I was a freshman and I didn't know what I was doing. So I kind of just designed it. You're free to play around with the design of the fin. Play around with the angle that it's at, how far back you want it swept, which also affects massively your stability. You see how it's increasing here. You can also affect how big it is and stuff like that, and how many you have. As I keep increasing, obviously the stability is going to go up. So it's just things like that you guys have to keep in mind when you're designing. And then the last two things I wanted to go over are these two tabs: your flight simulations and your motor configuration. To put your motor in there, you're gonna put select motor, new configuration, select motor, and then I believe for the L1, was it an H motor? Was it an H motor, or was it? Do you guys know? I forgot. I haven't done that in a while.
Sorry, picking up motor for the
For an
search rocket.
L1.
Yeah, I think it's one above it, or yeah, it's H and I's, I think, right, Joel?
H and
Yeah,
I's.
it's H and I just pulled up the thing.
H and I's, and then we will give you the ones that we have, so that you guys could pick out which ones you want according to your design, because we do have in stock. We're trying to mitigate stuff to order, so we're using what we have already in stock, and then you guys could pick out from those motors which ones you want to put in. Once you select a motor, let's say this one, okay, it inserts it into your airframe, and then you adjust your dimensions according to that motor. So you put the inner tube, which is your motor tube, forward, you move your centering rings and adjust them, and then you're set.
If I can just interrupt real quick. What Al was just talking about with motors is that certain types of motors require like certain types of certifications. So then each motor, the way that it's categorized is by its like impulse. So then lower impulse rockets, they can be purchased by anybody, but then as you get higher and higher impulse, they become like more and more dangerous. And in order to purchase them, you need to be certified. And then the way to receive those certifications is with you just apply for it, and then you have to launch a rocket as proof. So like if you're trying to build like the most basic kind of rocket, then you can use smaller motors, which then obviously they are less powerful than higher class motors. So like that's what I linked the wiki. It's just a classification of what the motor name means and like how they just relate to the performance of the rocket.
And then the way you get higher level motors is by being certified in and then getting different levels and stuff like that, so you get bigger and bigger motors and launch bigger rockets, and then that's why we're here, so you get certified. So so that's how you add a motor to your rocket, and then adjust your design according to it. Then you could also run simulations that give you a bunch of data, like the ground hit velocity and stuff like that. For the sake of it, I think I'm going to switch back to this one. Yeah. And then let's run a flight simulation. I have no promises that this is actually going to work because it's an old rocket, but let's see if it produces good results. So it gives you a graph of how your flight would look like. We'll get into this later. Later down the line. This is all, probably way too much information for you to deal with right now. So once you do that, it also, wait, where'd it go? Oh, down here. Okay, yeah, you see it came out, and then it gives you all of the values, and then It gives you a green if everything turns out okay. You also have to be careful because there's certain things that you wanna look out for, like ground hit velocity and stuff like that. You don't want it to be too high, because if it's too high, it comes down and it crashes into it, meaning your parachute didn't slow it down enough, or something's wrong with how you designed your rocket, and you have to redo whatever you decided to work out. So I mean, that's typically the basics of how Open Rocket works. We're gonna go deeper into depth with this later down the line in other meetings, and then in our design reviews, when you guys do have your own designs modeled out. If you guys have any questions based on Open Rocket, any confusion that you guys want me to clear up, or any of us to clear up, once, twice, 3 times. Chat's empty, so I'm assuming that everyone's good with it. And that's all I have. Does anyone else want to add anything? Joel, Bryce?
So next week we will give an introduction to flight dynamics. That'll be with Bilal. So I'm not sure exactly what his plan is, but I guess he'll be talking about like CPCG performance. He'll go a little bit more into how the motor affects the rocket. After that, I will be talking about the structure of the rocket. So I'll talk about like the materials and the fins and stuff like that. Then after that, it will be Bryce with avionics and recovery. So I think across the next 3 meetings, we'll just keep talking about just like how to design a rocket, then different choices you can make when designing that rocket to make it perform as you want. Then after like probably the next 3 meetings, we'll just be doing like open rocket workshops, and then yeah, from there we'll just make sure you guys feel competent and confident in your skills with designing a rocket from scratch.
And then making it, obviously, and putting it together.
Yeah, and I suggest if anyone here is just anywhat curious about Open Rocket and stuff, just give it a go. There's like a bunch of tutorials out there about Open Rocket, and a bunch of fun things you could do on it. It's pretty user friendly. So once you get past like just looking at kind of the ugly interface, it's actually pretty easy to use. And yeah, obviously me, Joel, Alex, and Bilal are here for any questions. You can honestly, after what you heard today, Leonardo, you could probably start making a model today.
Absolutely.
We're gonna go more into depth about all of the components you need on the inside of the rocket, because making the outer surface of the rocket, you could probably do that right now, like all the body tubes, the motor setup, the centering rings, all that. You could probably do. We'll go more into like material selection with Joel, flight dynamics, what you should be looking for out of a flight when you're running those simulations, and then avionics and recovery, how you're going to recover the rocket, because we don't just send the rockets up and hope that they come down all right. There's work that goes into making sure the parachute deploys and everything. We'll go more into those details later, but like for now, you could start on the Open Rocket. It's obviously like not expected that you come out to next meeting with your L1 done, but if you want to start theory craft and ways to make the rocket, yeah, we're all here to help you.
Yeah, we encourage it 100%. And I think that
Yeah.
it'll actually help you out a lot, because having a base, even though if it's not, even if the dimensions aren't completely correct and stuff like that with what we have, is really helpful, because we could just, go based off what you want for your cater to your rocket and your ideas and stuff like that. So definitely give it a shot. Open Rocket's kind of intuitive, as you guys saw. So there shouldn't be really much difficulty working it. If you guys do need help outside of it, you could always reach out to me and Joel and Bryce and Bilal, and we'll get back to you. I after 5 o'clock generally I'm free. So if anyone wants help designing their rocket, don't be afraid to reach out. I'm glad to hop on a Zoom call or Discord or something like that and help you work your way around the program and stuff. So apart from that,
yeah, so I think that's about it for today. Thanks for coming. And guessing most of these meetings they'll be next Thursday, every Thursday at 4:30 for the foreseeable future. I will try and get a room in the upcoming weeks, so that if we do Open Rocket, it's a little bit easier to troubleshoot it like in person instead of like each person trying to share their screen. It's just a little bit of a hassle doing that way. So just keep an eye out for that. And if you can't make it, like I said, or like what Alex said, just reach out to us and then we can probably try and meet on the side instead of like at these big meetings to just work on figure design or help clarify anything.
Also, make sure you guys all